great to see you, and I hope you're enjoying the series on the restoration of my new-to-me 60-year-old Heathkit PS-4 high-voltage power supply. In part one of the series, we had an introduction to the PS-4 power supply and a little bit of its history. We did an exterior inspection and condition assessment. We talked about the PS-4 front panel controls and what the power supply was expected to output. We also did a condition assessment and discussion on the interior top and bottom sides of the chassis. If you haven't seen my part 1 video or would like to review it, I have included a link to it in the description section below. When the third part of the series comes out, I will update the description sections in all 3 videos in the series to include the links to the other videos. I'm Steve, and welcome to my lab. As promised in my part 1 video, today we're going to be powering up the PS-4 power supply. I'm not sure when the last time it was powered up, and looking at all the original 60-year-old electrolytic capacitors in there, I'm a little nervous. And I think it would be wise that we bring it up on my current limiting dim bulb power source. If we get to full input voltage and haven't let out any of the magic smoke, we're going to try and put it through some of its paces. I might even be brave enough to take it to full output voltage and rated load, realizing that there's a very fine line between being brave and being very stupid. After that, if there is an after that, depending upon what we see and hopefully not smell, we will start on the supply's renovation. I'd like to start with changing the caps, but depending upon what we see during the power-up, we might start someplace else. So let's get things wired up so we can put some power to it. Before we get going here, I want to make it clear that this video is presented for viewer enjoyment and interest only and should not be considered as a comprehensive guide for knowledge, recommendations, or safety procedures, as errors and omissions may exist. If you are following along, you are doing so at your own risk. Items depicted, discussed, or envisioned in this video involve energized and charged electric circuits containing dangerously high voltages that could continue to exist long after the device is disconnected from its power source. If proper safety precautions are not known or practiced, damage or destruction to equipment or other personal property, fire, serious personal injury, or even death may result. It is strongly recommended that if you choose to work on any device shown in this video, you are thoroughly familiar with the design and limitations of that device and possess the tools and equipment to safely proceed. If at any point you have doubts or concerns, you should immediately stop, put the device in a safe state, and call a professional for help. Just a quick familiarization with my dim bulb tester so you guys know what's going on. I bring power into a kill switch. I'll show it to you later on. It sits up on my workbench, so when I'm powering something up initially, it's a trip-free switch that I can hit and I can kill power coming to the dim bulb tester. And by the way, I power everything off of this dim bulb tester even if I'm not using it as a dim bulb tester. So power comes in through the kill switch, comes through this on-off switch to these outlets that are grounded outlets. They're not isolated. And on these outlets is where I have my bulbs hooked up, so I can switch the bulbs in and out. So the bulbs are right up front. The current limiting portion of the tester is right up front on the main power. I come out of this outlet and I come into my variac. My variac, it's a 10 amp variac, 1.4 kVA variac. I have a bigger variac, but this works pretty nice. I have an 8 amp fuse in it, so I don't expect to go anywhere far with this. Out of the variac, I power this 2 kVA isolation transformer. It's pretty heavy, let me tell you. This guy is like massive. It's an old GE isolation transformer. I like it, but sometimes it's a little too big, I think. The output of this transformer comes to these 4 outlets that we see right here. I have a kilowatt plugged into it so that I can do things like monitor power coming through here. I also have this box. This box allows me to see, without tying up a meter, I can see the output voltage coming out of the transformer, the isolation transformer, or I can actually plug it in anything I want. I can plug it directly into the raw power before the isolation transformer if I want to. I also have the ability to jump into the circuit so that I can measure current with one of my flukes, right? And I can switch that function on and off if I want to. All right, but from here, as I come out of this box, I have another outlet, and I plug my device under test into the outlet of this meter. Now you'll see that everything kind of plugs together, so I can put things in any order that I want. There's a couple things I like and I don't like about this setup, and I'm going to be changing this, and we're going to talk about that in a future video. What I want to change on here. I kind of built this over many years, and there's things I like and there's things I don't like. For instance, these bulbs are right up front before I get to either the variac or the isolation transformer. So these bulbs see the charging currents of these transformers, which could be pretty high. So you know, when you select the bulbs you want to use for current limiting, I have to kind of consider what's going on in these transformers, and I'm not sure I like that. This metal box kind of scares me. I got a lot of shit laying in here, and if I happen to ground this box against this case, these outlets will also become grounded. So I have isolated ground outlet that I'm going to put in here just to add a little bit to the safety of the system, but this will work for now. So just so you guys know what's going on. Now what you're going to see is you're going to see this meter in the background up here. Again, I like this because I can get it. It's a fairly accurate meter, but I can get a rough idea of the voltage coming going to my device under test here. So, all right. So let's look at the setup from the PS-4 power supply perspective. The moment of truth is fast approaching. The first power up of my Heathkit PS-4 power supply, and I don't know how long. I don't know when the last time this thing was powered up. So we're going to bring it up gently and see what happens. In the background here, right there where my finger is pointing, we could see the voltmeter. That's part of my dim bulb tester, and we can see the two bulbs from the dim bulb tester. These bulbs, I have a 75 watt and a 40 watt. They're in parallel. Usually the way I pick my lamps, I usually pick wattages that add up to about 1/3 what I expect the device under test to pull. And I think this thing is going to probably pull about, you know, maybe about 0.3 amps or so, you know, 300 milliamps, you know, normally. And those two lamps add up to about an amp, right? So they pull about 3 times as much current as the power supply does. I find that's usually a good place to start off. We're going to find out. So what we're going to do is we're going to bring everything up to 60 volts on the meter, on the big meter back here. 60 volts AC input. We're going to look at the AC current draw, see what it's pulling at 60 volts. And I got a meter set up over here where we're looking at the B+ output just to see, you know, what it does. Obviously when we're running at some low voltages, the tubes could be anywhere. So we may see some strange voltage here, and that's okay, right? Normally you don't sit at 60 volts. So without further ado, let's get things going. Over here on the side, this is my little emergency switch, it's in the trip position. This is nice because it's got a an emergency button here that I can hit. And this thing, when I hit the stop button, it trips free. So when I release the stop button latches in. When I release it, it's still tripped until I hit the start button here. So let me hit the start button to apply power to my dim bulb tester. I got it set to 0 right now. I don't know if you heard the relay in here pick up. So let me go over and bring the voltage on that meter up here to 60 volts AC. Let's see what happens. Everything's on, ready to go. Bring the voltage up to 60 volts. You probably can't see that on the camera. That's about 60 volts right there at that division. The power supply is drawing nothing. Why is that? Because I have the power supply shut off. Oh, isn't that sweet? Let me turn it on. There we go. So the power supply initially drew about 220 milliamps, and now it's dropping down. The output voltage, as expected, is kind of going wherever it wants to go because the tubes are in some unknown state. Again, we have about 60 volts on here, and let's say it's at 160 milliamps, and let's let it sit for about 15 or 20 minutes. See how it looks. There's no smoke coming out. So that's a good sign. We'll let it sit for about 15 or 20 minutes, see how the current's doing here, and we'll decide if we want to go to the next step or not at that time. All right? See you in a bit. Okay, it's been about 20 minutes since we've applied 60 volts over here to this power supply, letting the caps form. They're 60-year-old caps. So the AC current draw here was about 165, 170 20 minutes ago. It quickly came up to this 180, and it's been holding there for, pretty consistent for the last 15 minutes. The lamps aren't lit up at all. I expect there's a pretty low voltage drop across them right now. So what I'm going to try and do is I'm going to turn up the variac to about 115 to 120 volt output. What I think is going to happen is these two lamps, it's a 75 and a 40, which is about 120 watts. So between the two of them, they're rated at about an amp. I think the power supply is probably going to come to, I think the power supply, when it's running at 120 volts, is probably going to pull like 300 milliamps or so. But I think in the configuration with the lamps and the circuit, we're probably going to wind up like around 250. So we're probably going to drop about 30 volts across the lamp, and there'll only be 90 volts available to the power supply, which should be plenty to heat the tubes, get the tubes to emission, and we might even be able to play around with the voltage a little bit. The voltage is still reading pretty funny because some of the tubes are probably just barely in emission, doing whatever. It's at such a low voltage. We can see I can see that the power lamp here is lit just a little bit. So without further ado, let me turn the variac up to what's normally about 115, 120. And where do we wind up? And we wind up at about 90 volts. The lamps are starting to light a little bit, which is okay because we're sitting at 200. I thought we were going to wind up at about 250 milliamps. We wound up at 240 milliamps. So we're pulling a quarter amp through those lights, which would be about 25% of their voltage drop, which is interesting because that would be about 30 volts, right? 25% of 120 is about 30 volts, so that only leaves about 90 volts for the power supply. And so we're at 240. Let's let it sit here for another 15 minutes, and we'll decide to switch the lamps out or not. So 240 milliamps. We're sitting at about 9 volts output, again, not a big deal, right? You know, it's better than it sitting at 600 volts output, I guess, when it's turned all the way down. So we'll check it out again in another 15. Okay, so another 20 minutes has gone by. Our AC input current was about 240 when last we were here, and it's still holding at 240. We're still at about 90 volts AC input, 240 milliamps AC. The output is, you know, 9 volts. I guess, you know, that's not bad, right? I don't see anything funny. Tubes are definitely, I can see a glow in the tubes here, and I can feel some heat coming off here. Good heat, not bad heat, right? So I think what we're going to do is we're going to switch out the lamps and apply full voltage to this power supply, and let's see what happens, all right? I should be sitting at about 117 volts AC input when we're done here, so let's see, lamps off. Looks like I'm sitting about 119 volts. $385 milliamps. The DC output voltage is about 1.5 volts. Now that everything is coming to normal with the B+ turned all the way down. So I think we're in pretty good shape here, huh? Wow. Let me pull up a chair here, and maybe we'll try and turn up the B+ voltage, and let's see where it goes, just for laughs. So 385, 1.5 volts. I don't know if you can see that, or if there's a big, is there a big shadow on that? Let's see if we can get that so we can read it. How's that? Is that something we can see there, or is that garbage? That's a terrible light, isn't it? Wow. Okay, it's reading 1.5 volts. Let me bring this up. Let's bring it up to like 100 volts. DC output. There's 75. There's about 111. And look, the voltmeter's working. It's reading a little low. I wasn't expecting that after what the seller told me. So that's not too bad unless the meter's stuck someplace. Obviously we're not going to see any current because I don't have any load on here at the moment. So we're at 390 milliamps. Let's boldly go where no man has gone before. Let's go up to 200. It's about 205. The meter is reading probably like 192. Oh, that's not bad. And again, no current. We're at 400 milliamps. So this thing should go to 400 volt output, but it looks kind of suspicious where we're pointing right now. So let's go up to 300 volts. 300 volts right there, huh? Be careful, Steve. Okay, I'm at 300 volts, and the meter is reading, you know, I'm looking at it from a different angle than the camera is, and the meter's reading pretty close to 300 volts. Maybe the problem isn't with the voltmeter. Maybe it's with the current meter. I guess we'll see when we put a load on it. We're up to 400 milliamps. That's not bad. Let's go all the way to the top here. Let's be brave. So that's, the pot's turned all the way up, and I'm almost at 400 volts. I have, you know, I can set the zero and the span. There's some pots for doing that, and that looks pretty good. This meter isn't that bad as far as it's reading, and we're at 417 milliamps AC input. So, wow, I'm impressed. I don't smell anything funny, which is a good sign, right? So let me turn this voltage all the way down. Comes down pretty nice. See where the 0 winds up here? It's reading less than a volt. It's reading 0.6 volts. And that took about 25 milliamps or so to go up to 400 volts under no load. That's nice. Let's plug into the C- supply. And by the way, the commons for both of these supplies are common. You know, the same thing. That's turned all the way down. So let's see. Let's put the meter switch in the C- position. It's reading 0 output. Now this is a logarithmic pot, so probably right around there is halfway, and it's reading minus 15 volts. And it's hard to read because it's down at the bottom of the scale here. Looks like it's about minus 15. Don't forget, this is going to probably wind up, because there's no load under here on here. It's probably going to wind up in the 120 to 130 volt range, I believe. Let's bring it up to 50 volts, minus 50 volts. There's minus 50-ish right now. And the meter is reading maybe 45 volts. Let's go all the way up. So we can see that there's quite a bit of rotation on this pot, as we'd expect with a log taper pot. So let's see how far it'll go up. Look at the meter taking off there. So with the knob turned all the way clockwise, we're sitting at 125. I thought we'd wind up at about 125 to 130. So that was a pretty good guess, huh? And the meter is reading maybe about 120 volts. So this meter isn't doing that bad. That's interesting. We'll have to see what happens when we put a load on here, though. So let me turn that all the way down. Wow, that drops pretty fast through there, doesn't it? Just the last, as you'd expect a log taper pot to do, the last little bit of rotation makes a big difference in the output voltage. We can see that on the meter and how much I'm turning the pot. So it looks like we got pretty good resolution over, like 3/4 of the pot's travel. So that's pretty good. Sorry about the abrupt ending to that last segment. My camera battery died. It gave me about 2 seconds notice. So anyhow, I was pretty much done talking. I was probably done talking before I started, but that's okay. So what I've done now is I've decided to go for broke here, because it's always good news when you torture a 60-year-old piece of equipment that you have no idea when it ran last. So what I'm going to do is I'm going to do a quick load test on this power supply. And what I've done is I've put together we say that the thing can supply 100 milliamps. So 100 milliamps at 400 volts, I would need a resistor that's a 4K ohm resistor in order to draw 100 milliamps at 400 volts. And the reason this looks so big is that's also 40 watts. So what I did was I took a couple of power resistors that I had and I wired them up to give me a 4K load, and made sure these are 25 watt resistors. I wanted to make sure that I had enough capacity, that I didn't overheat these resistors. Hopefully we're gonna not have any problems with this power supply, but I guess we're gonna see. So here's a little bit of a test, right? So what we're gonna see is on my triplet here, I'm reading volts, 0 to 400 volts, and I'm reading on the bottom black scale. So just so you can get an idea, I'm on the 1,000 volt range, right? So straight up and down would be 500 volts. So 400 volts is going to bring us right about here. 200 volts is here. Obviously we're sitting at 0. This meter is looking at the load through this load bank, the current through this load bank, and this other meter here is looking at the draw on the AC supply. All right, I've been letting the power supply warm up for a while. Right now it's pulling 377 milliamps, and everything else is set to 0. So let's go to like 100 volts, and let's see what it draws, what happens here. So we can see the triplets picking up. And with this resistive bank here, I should be pulling about 25 milliamps, so I'm pretty close to 100 volts. Pulling 26 milliamps. Current draw went up to 550 milliamps on the AC supply. This is reading pretty close, like 90-ish volts, and the current meter isn't reading anything. Maybe that's the problem that the seller was telling me about, right? I would think that we should be reading 25 milliamps over here, and we're not reading anything. Those resistors already are getting warm. Let's go up to 200 volts. So it's around 200 volts. I'm eyeballing from a strange angle, even though this has a mirror scale. It's about 200 volts on the triplet. About 50-ish milliamps going through here, which is what I would expect for this load. I'm pulling 720 milliamps on the AC supply. On the top scale, we're reading almost 200 volts. So this is actually a current meter with a resistor in series, so I can change the resistance value to get this thing to read correctly. So that doesn't bother me, but it looks like this meter is completely dead. That's interesting, because I mean that's right in the circuit, so there has to be current going through it. Maybe the meter's stuck or something, so that's one thing we're going to have to fix, is that meter. The movement might be stuck because there's no way it can be switched out of the circuit. All right, let's go up to 300 volts. We're living dangerously. That's about 300 volts. We're reading about 290-ish on this meter. We know this meter is off by a little bit. Again, we're not showing any current draw, even though we're showing that we're pulling 75 milliamps, because this is in amps, right? So that's 75 milliamps through this 4K load, and I can start to feel heat coming off there. And on the AC side, we're drawing 885 milliamps. Boy, we're really living dangerous now, right? Because it's a 60-year-old piece of equipment. It's probably the first time it's been chugging in a while, and we're sitting at 75% of its rated load. So you want to be real foolish? Let's go to 400 volts. 400 volts. Actually, we're going to go to 100 milliamps, because that's the rating. And this resistor isn't exactly 4K. It's pretty close. So the triplet says we're sitting at about 400 volts on the 1,000 volt scale, which is the 0 to 10 scale. We're sitting right about 400. We're sitting at its rated current, 100 milliamps. This meter is reading about 385-ish, maybe. And we're pulling 1.052 amps right now. Let me just write some numbers down here. 1.053 milliamps. I'm just curious to see what the power is that I'm pulling. Hopefully I'm not going to hit the camera here. Let me see what my kilowatt says. It says it's pulling 102 watts. That's not bad. 102 watts on the AC supply. All right. So it looks like it can supply 100 milliamps after not running for a long time without any problem. It looks like the voltmeter is reading okay. Boy, there's some heat coming off of those resistors. This meter, I can scale this. You know, it's got a couple of precision resistors for scaling that. I can replace them with multi-turn pots that I have down in my private stock. So that'll be easy to fix. The current meter isn't reading at all, which is interesting. So we're gonna have to figure out what's wrong there. I don't smell anything funny. I can certainly feel heat coming off the back here, which you would over the back of some tubes. So it looks like it can. Looks like it's working pretty good, actually. I'm surprised. We should see how what the voltage output is. Let me change some things around here. Shut off the camera. Change a few things around, and we'll see what the voltage is coming out of the B+ here. Hold on a second. So now I have this meter set up to read B+ voltage, and I have the B+ voltage turned all the way down right now, and it's reading 1 volt DC. So, and I can tweak that in, and if you remember, we have a 0 and span adjust on that B+ supply. So right out of the box, it's reading 1 volt. That's not too bad. Let's turn this guy all the way up, see how far it goes. Not that we can't trust the triplet, but we got a digital meter. Let's read it on a digital meter, right? So that's all the way up. It's 390 volts, which is interesting because now we can't get to 100 milliamps. That's interesting, huh? Can't be the load of that. It's pretty close to 100 milliamps. So again, I can tweak the 0 and the span on this a little bit to get that to come in. But I mean, right out of the box, that's pretty good, right? So it looks like the 60-year-old capacitors and resistors are up to the task here. So this restoration might be pretty easy. Actually, what we're going to do is we're going to measure everything. I'm still going to replace all the caps. We're going to measure all the other resistors and things and change what needs to be changed. But I just, I think it's a testimony to the design of this thing. It's 60 years old. It looks like it's almost all original. And look at it. It's sitting pretty much at its design point right now. And looks pretty good. Looks pretty good. I wonder what happens if I remove the load. Let's see what happens. So the voltage goes up to 397, and I put the rated load on there, and it only changes by 2 volts. 2 volts out of 400. So that's not bad. That's not bad. I think that's well within the spec. Right, let's check that again. 397, 398. Put a 4K load, 100 milliamp load on it, and it drops about 2 volts out of 400. So that's what, about 0.5%? That's not bad. That's not bad. All right. So let me break this down. And we'll take a look at the C- supply. Boy, there's heat coming off of those guys. Wow. Let me set up on the C- supply. We'll put a 1 milliamp load on that. What'll give us 1 milliamp at 100 volts, and we'll do some testing on that just to see what the story is. Be back in a second. So now I've changed the setup a little bit to read the C minus output, and the C minus says that it's 0 to minus 100 volts at 1 milliamp. So I wanted to make sure that we could get to minus 100 volts with a load that would give us 1 milliamp, right? So what I did was, as I said, at 100 volts, what resistance would give me 1 milliamp? That's a 100K resistor, and what I've done is I put a 100K resistor across that output just to make sure that we can get there. Now, I don't know if you remember what we saw before was when there wasn't any load on this, on the C minus supply, we saw 125 volts. So now that we have a load on it, let's see what we get for voltage. Now, I brought the, with the triplet, you got to watch this because, or any analog meter, because I said this red terminal here goes negative compared to the black terminal. So you got to make sure that you got the right polarity set on any analog meter you use. Not obviously, it's not a problem on a digital meter, but on an analog meter, you don't want to be driving it downscale too hard. So I changed the polarity to minus DC, even though I could have just rolled the leads here, and I've got it on a different scale. So we're going to see how far this goes, and then I got another experiment for you that you might find interesting, or we all might find interesting. So anyhow, let's see how far this voltage goes. So as I advance the C minus, I can see that it's going to becoming more and more negative as I turn it clockwise, and a bit of rotation it on this pot, and we're only at minus 17 volts, and now it's starting to change pretty quick. Actually, I should have switched that over so that we can read it there. So when I'm all the way in the clockwise position, I get 100.3 volts. Right? It says minus 100.3, so it meets the spec of being able to supply minus 100 volts at 1 milliamp. I'm pulling 1 milliamp through there, and this meter here is reading it's reading like 95 volts, so that's not too bad, right? So that's good, right? And we can see from the rotation of the pot, one, it looks like it might be a little scratchy, maybe not. It doesn't look too bad on the triplet. It looks kind of spazoid on that voltmeter. But we can see I haven't turned it that much, and we've already dropped 70 volts. So we should get some pretty good resolution on this pot at the lower voltage settings, which is good. So, okay, now I want to do something else here, because I think this meter switch, the way the meter circuit is set up, and I'm going to show you this on the schematic later on, I said I can read either the C minus or the B plus power supply by throwing this switch, but I really can't throw this switch while I'm driving something, because what it's going to do is it's going to cause a glitch in the C minus output. Now that's what I thought when I saw the schematic, so let's give that a test right now. So what I'm going to do is I'm going to turn up, I got this monitoring the B plus voltage, and let's switch that over to B plus, and I'm going to bring the B plus up to, let's say, 300 volts, okay? And that's showing on this meter, it's about put it about 300-ish, okay? And on the C minus, I have it at 63 volts. Now, there's a resistor that I use for reading through this, because this is a current meter for reading voltage, believe it or not. There's a resistor that's in series with it off of this power source, off the C minus power source. But it also loads down this circuit. So it has to be in the circuit whether I'm reading on the meter or not. And it just so happens that part of that switching takes place through this meter switch, and I'm going to show you this later on. So I think that it's okay when the meter switch is in this position or in the B plus position, but I think if I move this slowly, now we're going to look at, this is the actual output voltage. We can see it on the triplet here, nice and clear. If I move this slowly, I'm going to see the voltage is going to change. All right, as I go, see that right through the middle position? Because that resistor isn't switched in anymore. It's not, when I'm in the middle position, the resistor is disconnected and I lose that load. So I need to be careful if I use this meter switch, and I don't know why you'd want to use it today. I think the meter is a cool thing, and probably in 1963, most guys only had one meter. They didn't have, I have half a dozen meters in the lab here, as I'm sure you do. All right, but so you know, just be aware that if you are using this meter switch to see what the voltage is, one, you know, it's only, you can only get so much resolution, you know, even with an analog meter. But I think the analog meter clearly shows that as I'm moving this switch, when I get to the middle position, you can see the voltage actually goes up as I slowly go. I'm in the middle, and now I'm on C minus. I'm going to go back to B plus. I'm in the middle, and now I'm on B plus. So that loading resistor is in the circuit when I'm reading C minus or when I'm reading B plus, but when I'm transitioning between the two with this meter circuit, it's not, with this meter switch, it's not in the circuit. So I just want to be aware that if I'm driving a control grid and I'm moving this switch, I'm going to see the tube output's going to glitch as I move this meter switch. Might be something that I don't want to do. Obviously, this meter banging around up here, because it's reading the voltage from one to the other, you know, we expect to see that banging. This meter here, though, is actually measuring the output, right? And it actually changes by quite a bit. It's changing by over 10 volts at 63 volts. So that's a pretty significant change, right? It's at minus 63 volts. In the middle, it's almost minus 75, and then when it's all the way over, it's minus 63 again. So just something to watch out for, right? You know, when you're, always want to know the limitations of your equipment. But boy, so far, I mean, if I wanted just to put this thing on the bench, you know, clean it up and put it on the bench, this thing is, with the exception of this current meter, this thing looks like it's performing pretty well. But we're not going to leave well enough alone. That's not the way we roll here, you know. If it's not broken, we want to make sure we break it. So anyhow, there'll be some fun things coming along. And just one more thing while I'm here is I'm going to disconnect this load resistor, right? Because I'm at 63 volts here right now. And just to show you that the load resistor does affect the voltage quite a bit. The load resistor doesn't change the B plus output. It changed it by 2 volts at 400 volts. I'm at 63. If I take this load resistor out, it goes to 82. That's a big change. That's a big change. Changed by 20 volts out of 60. That's quite a change. So, right, the load does affect the output of this. 63, 82. So, when we look at the circuit, I told you I was going to do a circuit review, and I'm going to talk a little bit about this meter circuit and how it's a little hokey. But I mean, you know, it supplies the voltage that it needs to supply. It's pretty simple. It certainly met the goal of being cheap, right? So, and doing the job. Shouldn't cost any more to do the job than it should cost. So I think the engineers were effective in meeting that goal. So, all right, I think we're going to start doing some troubleshooting, and we might start by looking at this current meter. All right, let me get everything shut off, and that'll be the next thing we look at. As we go through the restoration and possible troubleshooting of the PS-4 power supply, periodically we're going to be referencing the power supply schematic, which is shown here. This schematic is specific to the PS-4, although it's very similar to the Heathkit model IP-32 schematic. I said in my first video that the only difference between the two variants were basically cosmetic differences. I also think that there might be a difference in the fuse sizing. I think the IP-32 uses a 3 amp fuse where the PS-4 uses a 1.5 amp fuse. But other than that, they're identical. If you want to follow along with these discussions with a copy of this schematic in front of you, I've included a link to it down in the description below. So we said we were going to investigate the output, the B+ output current meter, and that's over in this area right over here. So I'm going to zoom in on that and we're going to talk a little bit about that, all right? So now we're zoomed in on the B+ output current meter, which is right here. What we can see is we have B+ output voltage. It's this yellow line, comes from the 6L6 output tubes, series regulator tubes, comes down, goes through the meter, and the meter here says it's a 0 to 150 milliamp meter, and we saw that on the scale of the meter, but I'm going to show you something different about the meter in a couple seconds. So it flows through the meter and appears at the B+ output on the front panel of the PS4 power supply. This would be the red binding post for B+ output. The green line is the common for the power supply. Okay, so this is the black binding post on the front panel. So if I put my meter or my load across the red and the black binding post and I adjust the B+ output voltage, I'll see 0 to 400 volts. At a nominal rating of 100 milliamps. This meter is directly in series with that. Right over here, I've included this, but this really has nothing to do with what we're talking about. To add to the confusion, it's actually part of the metering for, you know, the voltmeter. And this B+ that shows up on my drawing, but doesn't show up on the drawing that I gave a link for down in the description. It indicates the meter switch position and not the voltage that's on that line. So I don't want you to think that green line is at B+ voltage. This is showing the position of the switch. This is actually common, right? Circuit common. All right. So this meter is kind of interesting because the meter itself, the meter movement itself, can't handle 150 milliamps, and I'm going to show you what's done on that meter here in a second. Let me zoom in on this little diagram up here, and we'll talk a little bit more about what's going on in the meter. I've redrawn this 150 milliamp meter to show what's actually in the meter case, hopefully to make it a little bit clearer. Now this meter has a couple of failure modes that we saw when we did our load test that this thing was reading 0. And there's a couple of failure modes of this meter that would still allow current to pass through this meter, even though the meter isn't working properly. One of them is that the needle is stuck. Obviously, you know, the current can still pass through the meter without any problem, and still appear at the output or the front panel of the power supply. We're going to check to see if the meter is stuck. The other one is that this really isn't 150 milliamp meter movement, because you know, meters are kind of sensitive, kind of frail, and in order to make it so that it could handle 150 milliamps, the moving coil in the meter would have to be fairly beefy. So what's typically done is to take a smaller meter, a lower current meter, and put a shunt resistor around it. And that's what's actually in this meter. So the meter itself, the movement proper is really a 5 milliamp meter, and it has a shunt resistor that is a 0.69 ohm shunt resistor across that meter movement. Now the dashed line shows the case of the meter, so this resistor actually is in the case of the meter. And what that allows is, it allows 145 milliamps of the current flowing through the meter to flow through the resistor, while only 5 milliamps will flow through the meter itself, right? And these are full-scale currents. Now, the way I figured it out was I was able to see the resistor, and I'll show you that in some pictures coming up. It shows that it's a 0.69 ohm resistor, and using Ohm's law, I was able to determine what the characteristics of the meter would have to be in order for this entire meter to support 150 milliamps. So the meter could be burned out, right? It could be open circuit, and there still is a path around the meter for current to flow. So again, you know, the coil can be completely burned out, and we're going to take a look at a few things to see what the problem with the meter is. I tend to think that the meter is damaged and not that it's stuck, but we'll see that in a few minutes. All right, I'm going to show you a bunch of pictures of the meter and some of the troubleshooting I did on it to come to my conclusions. And if anybody wants me to go through the derivation of how I figured out the size of the meter or how this would work, this is very, very typical for reading large currents. Like, you know, when you see an amp meter that can read 25 amps, you're not pulling 25 amps through the meter, otherwise the meter would melt. So there's usually some kind of shunt around it, and the shunt resistor could be internal or external. And if you guys want to see a derivation of how that works, I can create a video on that. I'd be more than glad to do that. Put something in the comments and kind of encourage me if that's what you want to see. All right, so let's talk about, I'm going to show you the meter movement taken apart, some of the troubleshooting I did on it, and the conclusions I came to. And what's a YouTube video without the obligatory action shot? Yeah, it's real exciting watching me remove the screws that hold this meter in place. Comes out nice and easy. But you already know that, otherwise you wouldn't be here watching this. And what I did was I just hooked my meter between these two, between the terminal here on the meter and this wire, and I was able to see the expected current flow through the load, and so I determined the meter was, there's something wrong with the meter. So there it is. We're going to take it apart and see what we can find. So a quick look over this meter. Looks like the needle isn't stuck. It is moving a little bit as I tap it, which is a good sign. Gonna look it over. Here's something that makes me a little nervous. If you look right here, that's interesting. You see the way that's discolored? Let's see what we got on the other side. Yeah, we got the same thing on the other side. Looks like somebody might have been here before, and possibly they couldn't get this cover to stay in place, so somebody was kind enough to glue the cover in place. We'll have to see what happens there when we go to take the front cover off, because we're going to have to do that if we want to really look at the meter. The meter looks like it's in pretty good shape otherwise. Too many reflections in there. But we can see that. And that resistor, it doesn't look like it's smoked or anything. I mean, it's normally black. Don't think that it's burnt. It looks like it's in pretty decent shape. But let me see if I can get this front cover off that's been glued on. Thank you very much. See if I can cut that open without cutting one of my fingers off. And we'll come right back in a couple of seconds. So after a little bit of cutting between the cover and the body of the meter with my utility knife and this razor blade, and probably some swearing along the way, I cut it free on both sides, and I was able to get the cover off. For those of you not familiar how to take the cover off, there's a couple of tabs on the top and the bottom that you can pry open. You can use a screwdriver to pry the front cover off, and it comes off nice. Now you want to watch out. There's this zero adjustment piece that locks into this this tab that allows you to zero the meter. Right when you're zeroing the meter and you're turning that screw on the front, it's like a little eccentric cam that engages in this slot, and it'll move this thing back and forth, and you can see how it's moving the zero. Right? So it appears that the needle is moving. Actually, it's a pretty strong return spring on that. I'm kind of surprised. But there doesn't appear to be anything funny here in terms of, its motion. When I let it go, it comes right back. So I think the next thing I'm going to do is I'm going to take these nuts off the back, and when I take these nuts off, we'll be able to slide the movement out of this case, and we can just kind of see what it looks like. I'm not really too confident that I'm going to be able to do anything with this because the wires are really fine, and just looking through the case, I don't see anything that's outwardly appears to be wrong with this. I have had meters on other pieces of equipment, like I have a Sprague capacitor tester where the meter was stuck. The movement actually got stuck. There was a piece of garbage between the magnet and the coil that moves the needle, and I was able to clean that out and get the meter working right. I was kind of hoping that this needle was stuck. And by the way, you got to be very, very careful when you're playing around with these movements. They're very, very delicate, right? So I know somebody's going to jump all over me down in the comments for moving that by hand, but for the sake of this video, that's what we're going to show. So anyhow, let me pull the movement out of the plastic case here, right? And we can take a closer look at it. Just to show you what I'm doing to get this plastic cover off, I've loosened up. There was 2 nuts, one on each one of these studs. I've already taken one off. You want to loosen these up, and sometimes there's a washer behind here. Now you got to be careful. You don't want to turn these studs when you loosen these nuts up, because sometimes there's a fine wire on it or something. So you got to be kind of careful. When you look at these things, you can't bring out the vice grips and the Gorilla Tools. Otherwise, you might regret that. So once you get those off, then it should be a simple matter of just pushing the movement out of the plastic case. Bada bing, bada bang. And there it is. So we can see the resistor doesn't look smoked. Now the only thing that kind of troubles me is this resistor. It's a shunt resistor, so it's between these 2 terminals. So when I look at the resistance of this meter, the schematic says it's a nominal 0.6 ohms. And it's probably dominated by the sizing of that resistor right there. And seeing as that's across the terminals, if the meter was electrically disconnected somehow, because the wires are really, really small and they can break, when I looked at the resistance across this meter, I would see resistance that's reasonable. It's reasonable to 0.6 ohms. So I can have a completely disconnected meter movement and not know that just by looking at the resistance, right? So when you look at what's going on in here, and I'm going to maybe take some pictures and just kind of see what's going on. But when you got a meter like this, you got to be very, very careful. It'd be very easy to damage this. But it would be especially easy. It was easy to damage as soon as we took the cover off, and now it's it's frighteningly easy to damage the movement. So not that this one works and we have anything to worry about in that regard, but let me just take a look at this off camera, and I'll give you my insights. You can see there's some fine springs and fine wire in there. Might be pretty hard to see if there's a problem with it. So, and if there's a problem with it, I don't know what we're going to do. Well, I do know what we're going to do. We're going to say the hell with it, and we're going to go without the meter as long as current can pass through the meter. And even if it couldn't, I can just put a short across the terminals. But I think this power supply is going to wind up with a non-functioning current meter. So let me take a look at this a little closer, and I'll let you know if I see anything. Before we talk about what I found on my inspection of the meter, let's talk a little bit about how the meter actually works. This picture shows, basic meter construction. Consists of a permanent magnet, which is a horseshoe magnet with a north and south pole, kind of like the one you played with when you were probably in second grade. In between the two poles of the magnet, there's a moving coil. It's a coil of wire that's suspended between the two poles. Attached to that moving coil is a pointer that then points up to a scale. Now that moving coil will rotate when current is when you put current through the moving coil, and the rotation or the strength of the magnetic field around the moving coil is proportional to the amount of current flowing through the coil. Now the rotation of that moving coil is counteracted by springs that are located on both ends of the moving coil. So the more the coil tries to rotate, the more the springs will the spring rate will increase to resist the rotation of the moving coil. If we look at the second slide, we can see more of the parts that are involved in a real meter, and we're actually going to see a lot of these parts when we look at the pictures that I took during my inspection. We'll be able to clearly see the pole pieces as shown in figure A, the circular core between the pole pieces, which doesn't rotate with the movable coil. It actually is stationary, while the movable coil kind of fits around that and rotates. In section B here, we can see the spring and how it's mounted on the end of the movable coil. Now the power is fed to that coil through these springs. There's a spring at each end of the coil, and power flows in and out through these coils. And also the coil on one end, by turning the coil, I can actually set the zero. It sets the force, the spring force on the movable coil, and I can zero the pointer that way. Everything rotates on pivots as shown in point C. These are very low friction pivots. This is a very low force system. Doesn't have a lot of strength to it. Very, very low magnetic force involved here. So it being able to move very freely is important. If we look at the picture in B, we can kind of see the whole thing, all as one assembly. And this is kind of what it'll look like when we look at the pictures that I took. All right. So here's one picture. The first picture that I took. The green assembly that we see is the movable coil. The movable coil is wrapped around that circular core piece. We can kind of see it in the middle. We can see the pole pieces on either side of the coil, and we can kind of see there's a slot, there's a space, a circular space for the coil to rotate. We can also see the coil spring, that copper-colored spring in the center, and we can see that one end of the spring is attached to, in the lower left-hand corner, is attached to a metal piece that comes to the end of the meter, and it looks like there's a white wire attached to it, and in fact there is a white wire. We're going to see the other end of this white wire pretty soon. This is where positive power comes onto the coil through this spring. The next picture, just a different view. You can kind of see the pivot point. We can see there's a little bit of adjustment. We see a threaded brass piece kind of in the middle of this picture. That's where the pivot resides. Adjusting these pivots is obviously pretty tricky. I don't recommend you play with them. Sometimes you'll find, like older meters, when they drag a little bit, you might want to loosen up on this pivot just a little bit. Very tricky. Wouldn't take a whole lot of movement to really screw up the adjustment completely on this. So, but it is possible to adjust. The next slide, just a different view of the same thing here, showing how the pieces are kind of insulated from each other, again, so that we can put power onto the movable coil without worrying about it shorting against anything. This next slide shows the other end of the meter, the front end. We can kind of see the pointer kind of pointing off at like 3 o'clock and the word Heath underneath it. The negative part of this meter is actually the metal frame of the meter. So this coil is attached to the metal frame. We can see some dampers here at about the 9 o'clock position on this in this picture, and those dampers kind of add to the inertia of the system, so the meter doesn't swing around. It kind of damps the motion of the meter a little bit. We can see the coil. We could just barely see the coil in the center of the picture. Again, the coil is green. It's underneath the that coil spring, that copper-colored coil spring. We can see there's like a green coil. That's the movable coil right there. All right, and we can see the zero adjust kind of sticking up at like 12 o'clock in this picture. And it looks like there's a screwdriver kind of in the center of the picture. It looks like there's a screwdriver slot with a lock nut on it. That's how you would set the clearance and the pivot pin. Again, it doesn't take a whole lot to because it's such a low force system. If you tighten this up too much, the needle won't be able to move at all. So approach that, kind of carefully if you have to do that, if you have to adjust that, or you think you have to adjust that. Just another picture again of the pointer end of the meter, showing the coil spring. So there's a coil spring on each end, on the pointer end of the meter, and also on the back end of the meter where the terminals are for the meter. All right. So what I was doing here was I was looking for any potentially broken wires or anything that looked kind of funny. This moving coil rotated very freely as I moved the needle, so there wasn't any garbage in between the pole pieces and the movable coil. From what I can see, it didn't look like there was anything that was damaged on the coil. It's really hard to see. Again, it looked like all the connections were made, so it's kind of hard to tell, and I don't necessarily have the best vision, which makes that a little bit harder to see, but I couldn't see anything wrong there. So what I decided to do was I came around to the back side of the meter, and at the back side of the meter, we have the meter shunt resistor, which is this black resistor. It's connected between the two terminals, which we can kind of see on the bottom. I have alligator clips on those terminals right now. I'm actually using those clips just to hold the meter so I can inspect it. To the right side of the meter is meter and shunt negative terminal. They share a common negative terminal, and in fact, the whole metal part of the meter is connected to the negative terminal. On the left side of the shunt resistor, we can see there's a white wire, and again, there's one of the terminal pins is right below that. One of the meter connection points is right below that. The white wire is the positive wire that goes to the meter movement. That hooks up to the coil spring on the non-pointer end of the meter. That applies positive voltage into the moving coil. The connection on the pointer end of the moving coil, that spring, connects up to this metal frame of this meter, which ultimately connects back to the negative terminal that I'm showing on the right side of this picture. All right, just so you can see that where the shunt resistor is mounted, It's actually inside the meter itself. Doesn't need to be. I can mount it on the outside just as easily, but this thing came as an assembly. This meter came as an assembly rated at 150 milliamps. And again, through this shunt resistor flows, of the 150 milliamps, 145 milliamps would flow through this shunt resistor. Here's a close-up of the shunt resistor. It's a 0.69 ohm, 1% resistor. It's well within its rating in terms of its power rating. It's a precision resistor. Again, it kind of helps determine the accuracy of the meter. So, if you hand selected, a crummy resistor, it would probably work just as well. But, that's just the way they put this thing together. So here, what I did was I said, okay, what I want to determine is the meter movement itself, is there a problem with the meter movement itself? So previously we saw the white wire, which I'm showing is the disconnected meter lead here. The white wire was connected up to the left terminal where the shunt resistor is. I disconnected it, and I measured the meter movement resistance with my fluke. All right, so I just hooked up to that white wire, and I hooked up to the terminal on the back side of the meter, the right-hand terminal. Again, that right-hand terminal is, I could have hit any metal part on this meter. It would be the same point. That was just an easy point to connect to. And you can see that my fluke is set for resistance, and it's showing overload. So that means the coil is open circuited. I did some calculations on this meter, and I calculated that the meter should be 20 ohms, and it's reading overload. So I think there's a problem with the moving coil. There's an open in the moving coil of the meter. So just to make sure that the meter could otherwise pass current, I decided to measure the shunt resistor, the resistance of that, just to see what that was. So you can see over the black lead, there's a wire kind of sticking off. Might be a little hard to see there over the black test lead, but I measured the resistance of the shunt resistor, and it's supposed to be 0.69 ohms, and it measured at 0.6886. Pretty damn close enough for what we're trying to do here. So what I concluded from all these measurements is that I can leave this meter in place with the wires hooked up, because the current will just pass through the shunt resistor without any problem. There'll only be about a 1/10 of a volt drop across the shunt resistor in this meter. Not a lot of power will be. There won't be a lot of power released, a lot of heat released across that resistor. And I'm just going to leave the wire for the coil, I'm just going to leave it disconnected. I'm going to look for a new meter, and basically I'm just going to look for something that looks kind of the same, something that I can change out the faceplate on, and whatever the current rating of the meter is, I know that I can calculate a shunt resistor and replace it later on. In the meantime, I can just use one of my other meters to measure the B plus current if I feel there's a need to do that, and I think that's about all that I can do for now. So, all right. So that's the deal with the meter. This video is already a little longer than I had hoped it would be, and be nice. I can hear you out there agreeing with me, but just bear with me for a couple more minutes. Before I start taking everything apart, I think I want to test the two voltage regulator tubes, the OA2 tubes we talked about in part 1. We said those voltage regulator tubes are nominally 150 volts, and they supply various references, biases, and they also supply the voltage to the the C minus output terminals. Now, the voltage regulator tubes are cold cathode tubes. They don't have any heaters on them. And I'm not aware of any way that I can test them on my tube tester. So I figured before we take everything apart, we'll just power up the circuit, see what the voltages are. I'm going to show you how to do it. Back to the schematic, so I can show you where the tubes are that we're going to be testing. There are these two tubes right here. This is V1, this is V2. These are 150 volt nominal voltage regulator tubes, and we're going to show you how to test them. I want to, because I can't test them on my tube tester, I want to make sure that I can make sure that they're okay. I'm pretty sure they're okay because we saw the whole regulator work nice, but just to see how far things are off, for the sake of completeness. So anyhow, we'll talk about those guys right there, all right? To give you a better idea of where we're going to be measuring, I took this picture from the bottom side of the chassis. Now the front panel would be at the top of this picture, and the two tubes we're going to be measuring, V1 and V2, they're OA2 voltage regulator tubes. V1 is on the left, V2 is on the right, and we're going to be measuring voltages between pins 5 and 7. Now pin 7 will be the negative side of the tube output, and pin 5 will be the positive side. Now the way these two pins are numbered is these are 7-pin tubes, and when you look at the large opening, the keyway, it's called the keyway, where there's the most space between two terminals, pin number 1 is the first terminal after the keyway, and then you count clockwise from there. Right, so in this picture, if we look at V1, pin number 1 is at about 7 o'clock. And from there, we measure clockwise around. So if you were to count the pins, you know, pin 5 is where I show there, and pin 7 is at about 5 o'clock position. Now, before you say something, when you look at V2, you'll see that there's no wires hooked up to pin 5 and pin 7, yet I could still read those. I could still read the voltage on those pins. And this is why. Here's a schematic of the bottom of the of a OA2 voltage regulator tube, the bottom side pin out. And again, the pins are shown going clockwise. Clockwise is the numbers will increase, the pin number will increase going clockwise. And if you look at it closely, you can see that pin 7 is actually internally connected to pin 2 and pin 4. Pin 5 is internally connected to pin 1. So as long as there's a wire on 2 or 4, I can read it on pin 7. As long as there's a wire on 1, I can read whatever's coming in on 1 on pin 5. Now let's look at the actual bottom of the chassis, and we'll take some voltage readings. So here we are in the energized circuit. I've been letting things warm up here for quite a few minutes, just so we get a good representation of what the voltage is on those voltage regulator tubes. Now I want you to realize that, like I said, this thing has been energized, and there's lots of scary voltages in here. Over here is 600 volts. We have 300 volts DC right here at the end of these two caps. Right here under the white, this was the AC fuse that had those exposed terminals on there. It'd be really easy to get the shock of your life off of that, so I just kind of covered that with tape. So right now we're energized, and you need to be very, very careful as far as what we're doing in here. All right. Now the two voltage regulator tubes, as you saw in the picture, this is V1 right there. This one is V2, and we're going to read the voltages by looking at terminals 5 and 7 on each of the two tubes. I need to read each of them individually because I just want to see the voltage off of that tube, off of that particular tube. All right. And we said that I can jump on the terminals on V2. We said even though there aren't any wires on there, as I showed you in the picture before we got here, that there's a lot of interconnects in the tube. So I could read the voltage on pins 7 and 5 on V2 and still get a valid number, right? So let me jump on V1. Got to be careful here. I'm a lot further away from everything than you might think, but still close enough that I can have a problem. And for some reason, the voltage isn't reading anything because I don't have the voltmeter plugged in. How do you like that? There we go. It's always good to plug in your voltmeter if you want to get a reading off of it. So V1 is reading 149.2 volts, which is pretty good because the 150 volt value that's specified for these tubes is a nominal value. And I'm guessing it could be off by more than a couple of volts. So I'm kind of surprised, you know, how close this one is. So this is V1. That's really good. All right. Let's jump over and look at the voltage on V2. And again, notice I'm jumping on terminals that don't have any wires on them. But again, there's interconnected wires inside. This one's reading 146.9 volts. Again, I think that's pretty good. I think that's really good. All right. So I'm going to say that these voltage regulator tubes are acceptable. I can't check their voltage regulation. I don't know how much current we're drawing off of each of these tubes, but suffice it to say that the voltage they're putting out is sufficient. Now, before somebody asks, if I didn't carry the ground over from just to look at V2 by itself, what I'd see is, as I look at the pin 7 on V1 to pin 5 on V2, what I see is both of those tubes are wired in series, 150 volts each, and I can see that together, when they're put in series, they sum together to 296.2 volts. When we went through some of our descriptions in part 1, we were expecting that to be 300 volts, right? So that's pretty close. So that's how you test 0A2 tubes, cold cathode tubes. Again, if somebody knows how to do that on a tube tester, put a comment down below. I'm not sure how to do this, but this is really good. It's in circuit. Shows us exactly what the tubes can put out, and I'm happy. Before this gets any longer, I think I'm going to cut it here. In part 3, what we're going to do is we're going to take a look at some of the internal components. Now, what I'm going to do is, before we get to part 3, I think I'm going to change out all the caps. I'll do that ahead of time. I already said we were going to do that, and I don't expect there to be too much problem. Maybe we'll test a couple of them to see how they checked out. But in part 3, what I think we're going to do is we're going to take a look at some of the resistors in the pots. We're going to test the tubes. We're going to test the rest of the tubes. And just generally give it a good cleanup, put it all back together, and fire it up. I hate to use that word, fire up. Hopefully that's figurative and not literal. But, you know, in part 3, we're going to wrap it up and see what it can do. Appreciate you hanging out with me, and hope to see you on the next one.